Welcome to the next webinar on modern Java by example. As promised, what we're going to do today is we're going to take a look at a variant of an example we looked at previously, where we created a completable future implementation of a web crawler used to be able to traverse recursively through a directory hierarchy, either based on a local computer or based on traversing through websites via hyperlinks. So let me go ahead and share my screen and I will get started. So let's share the desktop. And you'll see here that we have the GitHub repository. We take a look in the live lessons portion of this, go down here into RxJava, and you look down here in EX4, you'll find all the source code that we're about to talk about today. So that's where we're going to begin our analysis. So with that in mind, let's go ahead and switch over here. And now we're taking a look at the source code. The top level part of the source code looks very, very much like the earlier example we looked at with Completable Futures. The Completable Futures example is something we covered in a previous video. You can go back in my playlist and find the one that was the web crawler via Completable Futures, and that's where you'll find that code. So the top level code looks pretty much identical here. We go ahead and have a main program. We go ahead and parse the arguments, and we make a new image counter object, and that's where all the processing takes place. So with that, let us go down here and take a look at the code. So let's take a look at image counter. This is really the part that mirrors what we had done earlier with respect to the underlying RxJava, Completable Futures implementation. Okay, so as you can see here, what we've got is some fields. Some of these fields are very similar to what we had before. We have a field called mUniqueIDs, and mUniqueIDs is essentially a concurrent hash set. If you go over here and take a look in the utils folder, you see that there's the concurrent hash set, which is just a little light wrapper facade that encapsulates the underlying concurrent hash map class. So we just got rid of the value part of the key value mapping in concurrent hash map and just support the key part. So we use this field essentially to keep track of whether we've seen a URI before during our traversal, and if so, we're going to skip it because we don't want to do double counting or multiple counting. And this also ensures we don't end up with infinite loops in our call graph when we traverse through the recursive folder structure. The next field, we also had a field with this name in the last implementation. This is called M0, except last time M0 was a completed future that stored the value 0. And this time we're going to do something ever so slightly different. We're going to have ourselves a single, and single is very much like a completable future in Java 8. A single is a variant of an observable that only contains one element in it. And in this case, we're going to have it contain just the value 0. So essentially, this is a constant single for the value 0. And you'll see how we use this in just a moment to simplify some of the processing. All right, let's go down now and take a look at the image counter constructor. That's where the wheels get set in motion. The first thing we do is we go ahead and get the root URI. And as before, if you go and look at the options singleton, you'll see that we have a couple of different starting points. You can also override this if you want, but the couple of starting points are either the path name into the file system, into our resources folder, which you can see over here, or it's basically a URL to one of my websites. So either way, one is local, one is remote. They both look the same, and we encapsulate this inside of another little wrapper facade around the JSoup HTML parsing library. Option singleton does all the sort of obvious things. We keep track of whether we're local or remote with the URI that we've got. And here you can see that we have some option parsing where we can say whether we want to be local, whether we want to be remote, whether we want to give it a URL, if we don't want to start with the one that we've been given here as a value. And then you also can see here that we go ahead and use the max depth field if you want to set that, so you can prevent the crawler from crawling indefinitely. You can say, don't go further than n levels deep. I think we've defaulted to 2 or 3 here. Okay, so that's just a little bit of the options background. That's just a simple singleton class, nothing tricky or fancy with that at all. Now let's get into the heart of this thing. We're going to call a method called count images. We'll look at that implementation momentarily. And you can see that count images takes the root URI at this level and the depth, which starts out at 1, and then it goes ahead and recursively traverses everything starting from the initial point. And what we get back, of course, is going to be a single, and we're going to go ahead and use a blocking get on this single. So blocking get is just a way to wait until the operation is done, and then we get the result back. In this case, it's going to come back as an int. We could have also used blocking subscribe, but that was kind of overkill for our purposes here. So I used blocking get instead. You can think of blocking get as something equivalent to a terminal operation in a Java stream, or like the join operation a little bit in Completable Futures. Same basic kind of idea. And what we do here is we print out the depth, which is, this is the initial depth 0, because of course we're Java and C++ and C programmers, so the first level is always 0. People in Europe tend to have the first floor be 0 too. And down here you can see we print out the total number of images that were reachable from that particular root URI. All right, so far so good. This doesn't look a whole heck of a lot different from the Completable Futures version, really. So let's go down here and let's take a look at the count images method. This is what we just called. So count images takes the page URI and the depth, and as you can see, it returns a single to an integer. So once again, single is very much like Completable Future. We come in here, this part looks pretty much identical to the Completable Future version. We check to see if the depth is greater than the max depth. And if it is greater than the max depth, then we go ahead and we will print out the fact that it exceeded the depth. And then we're going to go ahead and return M0. So just think about this for a second. In that particular case, we don't actually have anything that we want to count because we've exceeded the max depth. So as a consequence, we're going to return M0. Likewise, the next thing we do is we check to see whether or not we've gone to visit a page URI that we've already seen before. And if we have seen this one before, we're also going to skip over it. So if we've seen it before, we're going to go ahead and return M0. Remember that put if absent is a clever atomic check then act method defined on concurrent hash map, and therefore taken by our concurrent hash set wrapper around concurrent hash map, that will check to see whether or not this URI is already in the map. And if so, it'll just basically return false if it's already there. If it's not been seen before, it will atomically add it to the map and return true. So this is how we're going to know if we've seen it already. Okay, so this is just kind of getting the bookkeeping out of the way to make sure that we actually have to do some further traversals. So if we do in fact have to do further traversals, we're then going to come down here to the count images async method. And count images async takes the page URI and the depth, and then it does an asynchronous crawl of the page to find out the number of images on that page. And then it also does an asynchronous crawl of the hyperlinks accessible via this page. So we'll look at that. That's a much more interesting piece of code than what we've seen up to this point. If everything goes well, then we go ahead and print out the total number of images here are going to be whatever we came back with at this particular depth. And so we'll see every time you go through, you increment the depth by 1. All right, so let's go take a look at count images async. This is really where things start to get much more different from what you would see if you looked at the Completable Futures version. Although they do have quite a bit in common structurally, even though the actual method's called and some of the control flow is ever so different. So the first thing we're going to do is we're going to call the get start page method, and we'll look at that in a second. And as you can see, that's going to return to us a page observable. And of course, a page observable is actually a single that returns a single that holds an integer. So var here, I could have gone either way on this one. I'm going back and forth between whether I like the use of var or not, but this is basically what it is. So it's a single it's going to be a single integer. Whoops, it's not a single integer, a single document. So that's what the actual type is here. So some people prefer it more explicit. I've been having fun playing around with var. The jury is still out as to whether var is actually helpful or not. The good news is that with a modern compiler and IDE like IntelliJ, you can switch back and forth easily without having to rewrite a lot of code. So let's go take a quick look at get start page just to kick things off. So we go down here to get start page, and you can see that get start page is going to use the single create factory method. And what that's going to do is the create factory method is going to go ahead and emit a single object. And in this case, what we're going to do is we're going to go down and call the get page method, which is part of the underlying JSoup library. So if we go over here and look at my little JSouper wrapper method, you can see the get page wrapper method in the JSouper wrapper class, helper class, will take a look at whether we're going remote or local, and then it'll do the right set of things to interact with the JSoup HTML parsing library to start the wheels in motion. So basically what it's doing is it's opening up the file via a connection if it's a web-based interaction, or it's opening up a file if it's a local interaction, and it's going ahead and retrieving that. Well, that particular call, of course, is synchronous. So we're going to go ahead and wrap this thing up in an asynchronous operation. And the way we're going to do that is we're going to use the compose method, which is one of RxJava's adaptability or customizability features. And we're going to go ahead and compose this with what's returned from the common pool single method. And common pool single, if we go peek over here and look at common pool single, you can see that this method is going to go ahead and use the common fork join pool as the scheduler, and we're going to go ahead and subscribe this particular flow on the common fork join pool. So what that's saying is it's going to download the page in a thread, in a worker thread that's obtained from the common fork join pool. That's basically what that's doing. And that's just the way you do it in RxJava. If this was Completable Futures, this would be implemented using something like completable future.supply async. And so just a slight different way to do it. I like that way just a little better. It's a little bit more concise, but this gives you more or less the same behavior. Okay, so let's come back up here. What we get back from this, of course, is going to be a single. We call it page observable. I probably should call it page single or page S or something like that. It's a single observable. And then what we're going to do is we're going to take that single observable, and when that's ready, when we've gotten the whole page downloaded, we're going to fork off, and we're going to have one path running concurrently through this piece of code, and then this other path here will run concurrently through this piece of code. And that's kind of the forking mechanism that you can do with RxJava, just like you can do forking with Java Completable Futures. So let's take a look first at what we're going to do here. This is going to go ahead and get us a single to an integer which counts the number of images in this page. So the images that are in this page are obtained by essentially calling this method reference, which is called getImagesInPage, and we'll look at that in a second. And then we're going to go ahead and get the size of the data structure returned from getImagesInPage. And getImagesInPage, as you'll see, is just a very thin wrapper around a JSoup select method, and it's going to return something that's basically an elements object. And elements is just a collection, and so we can get its size down here. So we're going to look at getImagesInPage momentarily. But before we do that, let me just point out that once again, we're going to go ahead and use the compose operation in order to make sure that getting the images in the page, getting a count of the images in the page, will also run in the common fork join pool. So we're doing the same trick that we'd used up here in the start page implementation to run this concurrently. Okay, so let's go take a look at getImagesInPage, and that's just a little further down here. And you can see all this is doing is it's taking the page, which at this point would have been downloaded, and we're going to go ahead and select all the images on that page. So it's basically like a kind of a database query, if you will. And it's coming back with an elements object, which is just a collection that keeps track of all the elements that are in the page. Okay, so let's go back up here real quick, and you can see that that particular call will then run also in the common fork join pool, and when we're done, we'll just get a count of the number of elements. So that's pretty simple. And probably that won't take too long to run. It just has to parse through the elements that JSoup has downloaded in the page document and then extract out things that are the image tag. Much more interesting is this path of the code. This path of the code is going to use flat map, and you'll see why we're going to use flat map in a second. And we're going to go ahead and invoke the crawl links in page method. And crawl links in page, as we'll see momentarily, is much more complicated than this method up here, get images in page. Get images in page just looks at the local page and counts the number of tags that are image tags. Crawl links in page, conversely, is going to recursively traverse all the links reachable from this page, if any. There may be none, but if there are links on the page, then they'll get traversed. And so let's go ahead and take a look at this. And you'll see in a second why we return, why we use flat map here, because we're going to end up with a bunch of these things from recursive traversals, and we want to map them all back together again into a, essentially into a single, as you'll see when we look at this later. All right, so let's pop down here and let's take a look at crawl links in page. So crawl links in page takes a document and a depth, and what it does, now we're switching over from singles to observables. And you'll see in a second why we do this. The reason we're switching over from singles to observables is we're going to end up with essentially a stream of these results coming back, because we're going to go ahead and recursively traverse through everything reachable from this page. And there could be multiple such links reachable from this page. So how do we do this? We are going to use the from iterable factory method on the observable class. And we're going to go ahead and select anything on that page that's an href. So the href syntax here uses the JSoup mechanism to query this document, this HTML page, and it'll give back essentially an observable of the elements. So it's a stream of elements that'll come back to this observable. And then what we do is we use flat map, and we're going to take each of the hyperlinks that we found, if any, and for every hyperlink here, we're going to use this flat map concurrency idiom. And this is, again, this is the way things work with concurrency in RxJava, starting from the very beginning. And what we do is for each hyperlink, we're going to use observables just factory method to create an observable for this. Then we're going to go ahead and compose it using the common pool observable method. So now we're going to be working on an observable, as before we were working on a single. So we have a different factory method here. So again, the consequence is these are all going to run concurrently in different threads in the common fork join pool that comes from the underlying common fork join pool framework that's part of Java. And then what we're going to do is for each hyperlink, we're going to go ahead and we're going to call count images recursively. So if you recall, count images was what we had defined way back up here at the very top. This is count images that we had before. And so count images is what we use to check to see if we've exceeded the max depth, check to see if we've already seen the URI, and if not, we recursively traverse this thing. So what we're doing now, when we get way down here into crawl links in page, is we're going to go for every link on a page, if any, we're going to call count images recursively and start the whole process over again from that location. So we're going to get each hyperlink and we're going to start over from our crawl. And what we do here is we go ahead and increment the depth by 1, because of course we're going down by 1 now. And that's going to go ahead and count the images. And remember, count images returns a single, but here we want an observable. So what we're going to do is we're going to convert the single into an observable so that it'll work properly with the data type that we've got at this point, which is an observable. So flat map is going to map all those different observables back into a single stream of observable elements, basically in this case into a stream of integers, and that's what's going to come back. So we're basically going to get a stream of integers coming back from flat map. And then what we do is we use the reduce method. And reduce is very much like a terminal operation that you would expect to have in Java streams, except what this is going to do is this is going to return something called a maybe. So what's a maybe? Well, if it turned out that we had any hyperlinks on this page, then we're going to end up with a sum that will be the sum of all the hyperlinks. Even if there's only one hyperlink on the page, we'll get a sum, which will be the sum of those hyperlinks. And that's what reduce will do. However, it's entirely possible that there were no hyperlinks on this page, in which case reduce, when used with sum, will have no result. So unlike Java streams, where you put an initial value like 0 as one of the parameters to reduce, in RxJava, instead of doing that, they have this other data type they call a maybe. And a maybe is either going to have 0 elements or maybe more than that. So in this case, we're going to end up with a maybe, which is either a single or nothing, if that makes any sense. So a single has 1 item, a maybe has 0 or 1 items. And then what we do finally is we use the default if empty method, and default if empty will either return the single if we had one, if we summed it all up to a single, or if there was no value there, if the maybe was empty, then we're just going to return the default value of 0. So default if empty returns a single that either has 0 if there were no items, there were no hyperlinks to be traversed, or it's got the sum of the hyperlinks that we traversed, counting up all those counts that were done asynchronously. So that's as I mentioned before, that's kind of the workhorse method in this implementation. It's the one that does the most complicated set of things. So let's pop back up here to our count images async method. And you can see what we ended up with as a result of those 2 branches we forked off. One which is going to end up with a single to the images in page, and one which ends up with a single to the images in links. And then we take those 2 singles, and now we're going to call a method called combine image counts. And again, I deliberately left the code structure here to be very, very similar to what I did with the Completable Futures version. If you look at the 2 implementations, they're very similar. You can treat them as Rosetta Stones to compare and contrast them because they're so equivalent structurally. Just the implementation details differ because one uses RxJava, one uses Completable Futures. So if we go down here and we take a look at the count image or combine image counts method, you'll see what we do here is we use another interesting RxJava method. And this one's called zip. And zip is kind of like the then combine method. This particular use case is almost identical to then combine. It's a little bit kind of like the all of method, which is this arbitrary arity method in Completable Futures. And what we're going to do in this case is we're going to go ahead and take the images in page observable, and then we're also going to take the images in links observable. So armed with those 2 observables, then we're going to go ahead and basically zip them together. And what zip does is it basically will return a single that, when complete, will contain the results of summing these 2 observable values together. So that's why it's very much like then combine. So it's basically going to return to us a single which, when completed, will contain the sum of all the various elements, in this case, images in page observable and images in links observable. So those will be the 2 things that get returned here as the results. Okay, so you can see that what we're going to get back from this combined image counts is going to be a single, which will contain the sum of the images in page and the images essentially reachable from links in the page. And then that, of course, will bubble back up here, and that's what we return from count images async. And you can also see if something goes wrong, if an exception is thrown for whatever reason, go ahead and catch that exception and return M0. Okay, so that's basically the overall structure of the program. I think it's particularly interesting because it's equivalent in terms of behavior to the Completable Futures version. And if we go ahead and run it, you can see, in fact, it gives us the same results. You can see that it tells us, it keeps track of the depth. If we go too deep, it'll give us an error. So it does a whole bunch of cool things, and it gives the same results. So let me stop at this point and see if there's any questions that have come up while I've been presenting the material. So let's see here. Question. So compose map. Yes. So the question is are all these various calls with compose, are they all going to run in the common fork join pool? And the answer is yes. And let me go ahead and show you that. We'll go back and reshare the screen so you can see what's going on here. Let's pop over here. The way that compose works in the way that I've set it up here is it goes ahead and essentially encapsulates the subscribe on method. And there's two methods in RxJava that are relevant here. One is called subscribe on and one is called observe on. And there is no end of confusion if you Google subscribe on versus observe on in the explanations of what they do. I'm not going to disentangle the subtle differences between them at the moment, but I will tell you what subscribe on does in the way that we're using it. So you'll notice that all these methods here, like common pool single and common pool observable, they're both subscribing either singles or observables to be connected to the common fork join pool. That's by design. I did that intentionally. And if we go back to the code here and see how these things are called, you'll see if we look down here, we have stuff like, page observable.map.compose.map. And the way that the .compose with the subscribe on mechanism works here is that will ensure that everything above this subscribe on will run in the common fork join pool. So in other words, the map method that's up here will run in the common fork join pool. And also everything after this method will run in the common fork join pool up until the point where we hit another subscribe on or observe on. So this is typically done in programs, say like Android, where you want to run some things in the background. Like you might want to do your I/O in the background. So you would subscribe on things to run in a background thread in, say, the common fork join pool or a fixed size thread pool or whatnot. And then you want to have it observe on the main thread. And so if you see the RxJava version of Android, they've extended it to basically have another scheduler, which is the main thread scheduler. I forget whether I think it's called main or something like that. So you can actually have a little pipeline of operations, and you can then dictate the threading context in which those operations run, and then the RxJava framework magically under the hood will move things around to the right place. So that's very cool, very powerful. It's actually a little bit seductive in a way because it's so easy to write code that will run things on all kinds of different threads, and it looks very easy syntactically, but you could have some performance surprises if you're not careful, because there is a cost of moving things back and forth between the threads. But yes, to answer your specific question, putting the compose here will cause this map operation above to run in the common fork join pool, and this map operation below will also do that. And chances are they're likely to run, I almost guarantee you they're going to run in the same thread because they're just very simple synchronous operations. In fact, in some of these cases, I could actually put the compose method after page observable and before the first map, but you have to be a little careful there. This is the typical way you'll see it used if you read about RxJava. Okay, so that's what I wanted to cover with the RxJava stuff. Now, just for kicks, let's go back up here and let's see if we can open up. Let's see, we'll probably have to open a project. And then, of course, half the time it forgets where I was. So we'll go ahead and click down here. And we'll find my live lessons folder. And then let's go ahead and look at the image counter. This is the one that's this is the implementation that uses Completable Futures. So let's go ahead and open this as a project. Hopefully it'll pop right up. And also sometimes things get confused and it loses the SDK. Not quite sure why it does that, but should be happier now. So this is the RxJava version. And I know we covered this the other day, so I won't dwell on this at length, but I just wanted to quickly go through it now that we've seen the RxJava version and just give you a sense of how they kind of compare and contrast with each other. So here's the Completable Futures version. If we run it, we should get hopefully identical results, and we do. So you can see that it gives us the same results that we did before. The threads may be a little different, but under the hood, it's basically the same thing. I haven't had a chance to really test the performance of these two implementations. I would suspect to be very equivalent. But here, again, really fast is the Completable Futures version of all this stuff. So you can see here, we have our concurrent hash set. That's the same as before. We have M0, which is now a completed future to the constant value 0. So it's pretty much the same as that single we looked at before. We do something similar. We call the count images method. We handle the results if there's exceptions or if it succeeds or fails. And then we use join. Join is kind of like the blocking get method we used for the RxJava version. Then down here is count images. You can see we first check to see if we've exceeded the depth and return M0 if that's the case. That's identical. We check to see if we've seen the URI before. If so, we return M0. That's identical. Then we go ahead and count the images async. That's the same as the RxJava version. A little bit different way of handling the results, but semantically equivalent. Here's count images async. You can see that this returns a completable future to an integer as opposed to a single to an integer. But again, very similar in structure. We get the start page. That's the same as before. We use var. In this case, of course, this is a completable future to document. So that's the same as, essentially the same as the version from RxJava. Now we've got that page future, and we can go two paths. We can either go to get the number of images on the page or get a count of the number of images reachable from the page. This is very similar to the RxJava version. The difference is we don't have to use that compose weirdness that we do with RxJava with subscribe on, because the concurrency semantics are baked into completion stage methods in Completable Future. So it's just a little bit more concise. You can see that down here again as well. We just make a call to then compose async rather than flat map followed by compose followed by subscribe on. So as a general rule, Completable Futures and parallel streams are a little bit more concise with respect to designating when things should run concurrently. But otherwise, the structure looks almost identical. We combine the image counts together very similarly. Here's how we do it with Completable Futures. We just use then combine as opposed to zip, but it's almost identical. Here's get start page. This looks very much like the RxJava version, except we use supply async as opposed to create followed by compose and on subscribe. But again, with an epsilon of being identical. Get images in page, it's identical. Crawl links in page. This is a little different in terms of the syntax, but the behavior is pretty much equivalent. We go ahead and select all the hrefs on the page. We get back an elements object. We convert that to a stream. Then we use the map method to go recursively traverse everything using count images. That's going to return a stream of completable futures to integers. Then we go ahead and collect everything together using the stream of futures collector that we've talked about before. This kind of plays sort of the role of flat map a little bit in RxJava. And then when that's finished, we go ahead and apply this action, which takes the stream that we got back and then reduces it. So I think you'll agree that structurally these two programs are very similar. You can see how singles in Completable Futures, single in RxJava are pretty much like Completable Futures in the Java Completable Futures framework. And the difference is kind of in the details. And the differences in the details having to do particularly with how you express concurrency. In Completable Futures, it's a little bit more streamlined. With RxJava, it's a little bit more idiomatic, if you will. But, a good programmer should feel at home with either one. So that's what I wanted to cover today. Let me just go over here and give you a preview of what we're going to cover tomorrow. So tomorrow, we're going to go ahead and look at yet another interesting RxJava example that has an equivalent Completable Futures version. And this particular example is going to show how to do timeouts with RxJava. And so this example is basically doing the web service example I looked at a little while ago, maybe a few days ago, where we're going to get the price for a flight from London to New York with one asynchronous operation. And in parallel, we're going to get the exchange rate in pounds versus dollars in another asynchronous operation. When both of those values come back, we're going to go ahead and then produce a result, a price for the flight leg. And if we have timeouts, then we handle those in various ways. And so I'll show you how to do that with RxJava tomorrow. And we'll probably also spend a few minutes kind of comparing and contrasting with how that works from a completable future point of view. You'll see once again that there are sort of pros and cons of each approach. And this particular example is kind of fun because it also uses it uses some other interesting features to show how all these different things work. Okay, so that is what I wanted to cover today. I think there might be another question. Let's see, the Reactor framework by Pivotal. Do you recommend it instead of using RxJava? I haven't really played around with the Reactor framework enough to render an opinion one way or the other. I've got to kind of believe that looks very similar in a lot of ways to what we've been looking at here. One of the things you discover as you play around with Java streams and parallel streams, Java Completable Futures, you play around with RxJava, once you kind of pop your mindset into this sort of reactive, functional programming style of writing applications, they're very, very similar. And mostly they just differ in terms of, the way in which they allow certain things to happen, and also, how easy it is to do certain things like handle concurrency and handle integration with other frameworks. So I haven't played with the Reactor framework yet. That's probably something I'll take a look at. Many years ago, I wrote a pattern called the Reactor Pattern. And so I'm interested in knowing the relationship between the Reactor Pattern I documented 25 years ago or so and the kinds of reactive computations that the Reactor framework supports. Obviously, the Reactor framework here by Pivotal does more interesting things than my Reactor Pattern, but it's kind of fun to see how the world has evolved with respect to reactive programming. So with that, I thank everybody again for joining. This video will be uploaded shortly to to my YouTube playlist, and lots of people have been going there and watching the videos, so that's fantastic. So I'll keep this going for as long as there are people who are interested in getting a chance to watch me talk about these interesting topics. I'm also considering at some point perhaps doing a C++ standard template library tutorial, because I've also got lots of material on that as well. And if you're a polyglot, if you're someone who does Java and C++ and JavaScript or whatever, chances are you'll get a kick out of that as well. Again, thanks to you guys for showing up and joining, and I will look forward to seeing you again soon.